Okay, now we get started again. My point about that part is, students email faculty all the time and say, what's the best way to study? What do you think is helpful? And we give you advice, and we think it's good advice, but ultimately, you can provide the best advice to each other. I typically think reading the book 5 times doesn't help. It's not really that valuable. I usually think rewriting your lecture notes, thinking about the slides, talking about them out loud, being an active learner is the best way to learn this material. That will especially be true for the lab exams. Now, you have 5 exams in the exam reader. I suggest you try doing one. I suggest you take it in 100 minutes and actually grade it and see how you do. If you get 50, don't be surprised. What you'll do is you'll learn, I didn't quite think about it this way or that way, okay? Now, most students, when they take a math class, they do the homework, and they would never dream of taking an exam without doing the math homework. The same is true about biology at this level. You need to draw out PCR. You need to draw out mitosis. You need to draw out meiosis. You need to think about ploidy and what the number of genes means and loci and things like that, okay? It's really beyond this part where you just memorize things. You have to start to be able to use it as a language, okay, if you want to be successful. Anyway, so for this week's lab, you've been streaking out the colonies, so you're done with that. This week, you're actually going to do the PCR reaction, which is using the Taq polymerase, denature, and neal extend for 35 cycles. So hopefully we'll get a large yield of DNA. We'll check that out next week by running the sample on a gel, and we should see bands of particular sizes, and then we'll use the amount it fluoresces or the color of it to determine how much DNA is in that band. So it'll be quantitative. So the gel will do 2 things. Both qualitative to tell us we have a band of a given size, but also quantitative so we know how much is there, okay? And then once you know that, we'll set up sequence reaction. So today I will talk about sequencing, how it works, because we don't have much time next week. So this week's lab, you will be looking at an autoradiogram. It's already been a gel that's been run. It was radioactive, and you'll determine the sequence from that. Next week, you'll send out, once you know your samples, you'll set up the sequencing reaction. We'll send out your sequence back later, okay? So I'll talk about mitosis, meiosis, and of course the DNA sequencing. Now I looked at the syllabus. We are way ahead of the 1A class. Normally we would have already done mitosis, meiosis in the 1A class. I don't have enough time to go over all the stages of it. Dr. Patel will have more time, all right? So anyway, please do the reading. So photosynthesis review, a couple of quick things. Is here. This is what the data should look like last week, hopefully. And a few things about this. All right, so we had a blank, which had chloroplasts in it, but no DCPIP. So that when we added the DCPIP to our actual reactions, when we added the DCPIP, we added the blue color. The blank didn't have that. So once we added the blue color to DCPIP, we had a high absorbance. If we don't reduce the DCPIP, it remains blue color, and absorbance is high. So in the dark, we should expect this not to change. In the presence of dichloromethylurea, we also expect the values not to change, because if you remember how the electron transport chain is linked here, we have photosystem 2, and then we have the electron transport chain, and it's electron transport chain that's pumping protons into the thylakoid space. So this is the membrane. If we want to think of this as one layer of that bilayer, and here's the other layer of that bilayer. And remember, a given thylakoid looks like this. One layer here. So this space corresponds to this space, the thylakoid lumen. Then we had photosystem 1, and then that donated electrons to NADP+ to give us the reduced form, or in our case, we saw DCPIP being reduced. Dichloromethylurea blocks electron transport here. So as a result, since we're measuring the reduction of the DCPIP in the presence of dichloromethylurea, we shouldn't see much of a drop. Now you might see an initial, very small amount of drop, because photosystem 1 can still reduce the DCPIP. But the amount of photosystem 1 is very small. The way photosynthesis works is it keeps cycling and cycling. So the size, in terms of amount of molecules, this is very small, so most students don't see that slight dip, okay? Now, as electron transport chain is working, if there's no DCMU here, we expect to make more and more of a proton gradient. And as a result, to pump more and more protons takes more and more work. So if we have that methylamine, which acts as a pH buffer and grabs that proton and removes it from solution effectively, we no longer have a proton gradient. We're not measuring ATP production, we are measuring DCPIP reduction. And as a result, the electrons can actually go faster through the chain because it's not working against the gradient, and that's why in the presence of methylamine, we should see a faster rate of reduction. So this is methylamine there, and that's the light reaction. Faster because we don't have that back pressure. Is that clear? Now realize the parameter measured here was the reduction of DCPIP. You should think about what this graph would look like if we measured oxygen production or maybe ATP production. So I want you to take a minute right now and draw what you think these graphs would look like if you're measuring oxygen production. Feel free to talk to each other. Learning is collaborative. Okay, let's take a minute to discuss this. So in the dark, without photosynthesis, and remember, where's oxygen coming from? It's coming from the lysis of water to yield oxygen, the 4 electrons, and the 4 protons. And it's these electrons that are reducing the oxidized reaction center to allow the process to continue, right? So we effectively, in linear photophosphorylation, we're transferring electrons from water all the way normally to NADP+. So in this case, since we're measuring oxygen production, in the case of dark, it should be effectively non-existent, right? Because we're not going to do the light reactions. In the presence of dichloromethylurea, it's going to be similar. In the presence of light, we should see some increase. And light plus methylamine, we already said this causes electron transport chain to go faster, so what should that do to the rate of oxygen production? Also faster. So in fact, the graphs look very similar, except they're inverse plots, okay? Think about what the graph might look like if it was ATP production. So on the lab exam, I may have already written it, asking you to plot ATP, okay? Any questions on that? All right, so question 6 here is from the worksheet, I believe, and I'm going to go over it with you now because there's always so many questions over this. Now, this is a situation where we have both DCMU and methylamine together at the same time as we expose those chloroplasts, that solution. So we have both DCMU and methylamine. So what do you think would happen in that case? Would it go faster? Would it stop? What would be the rate of reduction of DCPIP? It should stop, because what will happen is the DCMU blocks electron transport, so even though we have methylamine, that methylamine acts downstream of the block, So this is upstream in the pathway, so DCMU overrides the effect of the methylamine. Okay? And that will actually introduce the concepts of pathways because we'll be talking about histidine biosynthesis. So think about pathways, order of steps. Okay? Now, question 7 is one that is not meant to be a specific numerical value, but just a general trend. How much NADP plus is being reduced relative to DCPIP? When we take those chloroplasts and we've isolated them, and then we rupture them, the amount of NADP plus, so I'm going to just redraw this chloroplast, and I'm going to draw one line as a bilayer, and we have something like this. There is indeed NADP plus here, and when we break it open, it's released to the external environment. But also, remember, we added a large amount, half a mil, of a very concentrated DCPIP. So in fact, the concentration of DCPIP is way greater than this, probably 1,000-fold times more. Because there's a small volume of chloroplast. This stroma is a small volume of that. So half a mil of chloroplast is not a solid packing. So there's a small volume of chloroplast within there. Then this is a small volume within there. And then this is a low concentration. And we had half a mil of this externally, and it's a high concentration. So just relatively, there's a lot more of the DCPIP than the NADP+. Any questions on that? All right, so let's move forward on the Vibrio stuff. So hopefully you got that nice isolated colony. You're going to set up the PCR reaction. I'm not going to spend much time on this. I tried to lay the groundwork in other lectures. Just remember, we have a background. In this case, it's a bacterial chromosome. It's huge. And we're picking a small point on there, okay? And the way we can pick that small point is we already have information about the background, the genome of all those bacteria. And what we know is that conserved amongst all these bacteria, they have this large chromosomal DNA. It's huge. Double strand, circular. We know that this sequence and this sequence is conserved. That's why we were able to generate primers that will specifically target that specific locus. Likewise, we know these sequences here are conserved, which will allow us to specifically target that sequence. But it's a small subset in this big background, okay? And I showed you last time how PCR works if we had just unit DNA that we started with, we never saw non-units. But realize we will have some non-units increasing by 2 each round. So we'll separate those 2 strands. How do you do that? How do you separate the 2 strands? Heat it up. So if this is the DNA here, what holds the 2 strands together? Hydrogen bonds. So to break it, that was triple-stranded DNA, that's unusual. You just break the hydrogen bonds, just heat it up. So when you heat it up, it will separate easily. And granted, yes, it's a huge molecule. And it's separating and going back and forth very dynamically. But what happens is because we have those primers in huge excess and they specifically bind, you will get a small part, that primer will anneal specifically to that target. And that will allow us to start amplifying from that point. We can extend from that point, okay? So anyway, just keep in mind, heating, denaturation, separates the 2 strands, lowering the temperature and adding the primers are in there, allows the primers to anneal at specific points, and then we allow it to extend by heating it up a little bit. The top polymerase extends. We'll talk more about these primers, and then we yield 2 molecules. Start with 1 double strand, 2 double strands, 2 double strands to 4 to 8, always doubling, okay? And then this is something we've done before, just to introduce the concept of unit versus non-unit length. I think it will benefit you tremendously if you draw PCR out for 3 rounds of replication and indicate different primers, a forward and reverse primer, by 2 different colors. Okay, just draw it out. I think it will really help you to understand what unit length versus non-unit length is and why these increase exponentially and these always, the non-units increase by 2 each time, okay? We've gone over that a few times. This was the formula for this. Okay, we went over that last time. So I'm going to go over the PCR protocol with you a little bit, and we're going to go over the primers again, because when we do DNA sequencing, we will need primers as well. So I'll go over the structure of DNA then, show you the primers, show you what they're doing, and how they set the site, okay? So for the PCR protocol, this is for both targets. You're going to take the colony and you're going to suspend it. So you get an isolate colony, we have those sterile loops. This time you're using the needle end. Go in there, just stick it in the colony. That will transfer bacteria from the colony onto the stick part there. You'll stick that into 50 microliters of water, and then what will happen is the bacteria will just transfer, okay? All right. Now, I put this no boiling necessary because a lot of students are working in research labs, and they'll say to me, well, when we do colony PCR, we boil the samples. And it usually makes it easier to get the DNA out because boiling breaks open the bacteria, and breaking the bacteria open allows easier access for the primers, et cetera, et cetera. But we don't want to introduce another step of boiling in there because it's just too complicated. So in lab, you may do that. We're just not doing it, and it's not necessarily the way we set it up, okay? So the way this is going to work is you just basically set up 2 tubes. These are small volume tubes. The reason why they're small volumes is we have what's called a thermal cycler. Basically, the GSIs will transfer your samples, once they're properly prepared, into a metal rack, basically, and that metal rack will heat up and cool down. Heat up when it's denaturing, cooling down when it's annealing, increasing slightly, and then stay at constant temperature for the extension, okay? So these small tubes allow the transfer of that heat more quickly. So you're going to put 20 microliters buffer in the tube. Notice both types of primers, and again, these are specific primers in the sense that this is a pair primer for the 16S, and this is a paired primer for the RPOB, okay? If you do the forward primer here, let's call this forward, and then do the reverse one here in a pair, it's not going to work because you won't extend that far in a given 2-minute or even 30-minute cycle, okay? So they have to be paired primers for the target, okay? And then you'll just set this up. You'll take 5 microliters to suspend the colony as the last step. You'll give it to your inspector, and then they'll add the enzyme, okay? And then they'll transfer it to the thermal cycler. Any questions about that? And hopefully it will work. PCR sometimes works great. Sometimes it doesn't work so good. Okay? We try to optimize it to get as best results as we can, but there's a lot of variables we can't always control. How many bacteria do you transfer from your colony? How old was your colony? Was it really growing well? Was it stagnant? Racing like that phase of growth? We do the best. Hopefully it'll work. So anyway, these are just the primers here. Again, the primers will flank our target. And the primers are always incorporated in the end product because when we extend from here, this primer binds specifically, notice the antiparallel nature. So there's directionality to DNA. 5' 3' 1 strand, conversely 5' 3' this one. So the primer that anneals to this strand must be antiparallel, and it'll base pair here, and then we have created a 3' hydroxyl group there. DNA polymerase must attach to a pre-existing 3' hydroxyl group. RNA polymerase does not have that requirement, but DNA polymerase does. So the primer allows us to pick the start point, and it allows us to have that 3' hydroxyl group so the DNA polymerase can extend. Likewise, same thing for that primer, okay? We can make some frequency predictions. Now, this is involving some math. We went over it briefly last time. So if you had this sequence here and you have a genome of this size, how often would this sequence appear? So let's just take it for one strand, okay? So if the A is 25%, that means the A probability of that occurring is 1/4. Probability that a T would occur next to it is also 1/4, because percentage of A is 25. What's percent T? 25 what's percent C? 25 what's percent G? 25%. So it's a little easier to do the math. So the chance this A is 1/4, this T is 1/4, that C is 1/4, that G is 1/4, that A is 1/4, and that T is 1/4. So it becomes 1/4 to the 6th power. And 1/4 to the 5th is the same as 1/10 to the -3, or 1/1000. approximately. It's really 1,024, but we're just kind of rounding it, okay? But we still have another 1/4 here, correct? So to do the math easy, that's 1/4 to the 5th. That's another 1/4. So that's the same as 1/4 to the 6th. So it's 1/4,000, approximately. So that sequence should appear, if it's random throughout there, on average, maybe 10 times. Do you see how the numbers work? Because this is the probability of the event, which is 1/4,000, and we have 40,000 possible nucleotides. So it becomes the probability of the event times how many chances you have to do that. So it's approximately 10 times, okay? Now, not exact. Some sequences, take randomly, it may only appear 6 times. Other times it might appear 15 times. This is purely statistics, okay? Any questions about that? So let's try to do a little bit harder problem. And now the percentage is 20%. So I'll give you a minute to work on that, okay? So try it with 20%. That's the same as 20 over 100, okay? Is there a question? Do I need to? What? You know the percentage of A is 20%. That should give you the percentage of everything else. Okay, let's quick do this. So the percentage of A is 20%. What's the percent of T? Also 20%, because these base pair in double-strand DNA. So once you know one, you know the other. So that's 40%, which remains, the remaining 60% has to be C and G. So this is 30%, and that is 30%. So the question that came during the discussion was, could you tell us what percentage of these are? This one number is sufficient to tell you all the others. Is that clear? Because it's double-strand DNA and base pairing rules are followed. Now, the chance of having the A is 20 over 100. The chance of having the C is 30 over 100. The chance of having the T is 20 over 100. I hope I don't run out of space. Another A is 20 over 100. G is 30 over 100. And T is 20 over 100. That's the probability of the event. So how many times does it happen? Depends what size the background DNA is or the genome you're looking at, right? It's always the probability of the event times whatever our source DNA is, okay? Now, I wouldn't typically ask you to multiply this out, but on the exam I would have several possible choices for the answers. Okay? Does anyone need me to go over that again? No? Okay, great. Let's move on then. And we actually use those frequency predictions. If we have unknown DNA and we say, I'm trying to generate primers and I want it to occur maybe 10 times in the background, I can work backwards, okay? So anyway, that's what we just did, so you can figure out that out for yourself. That's just sort of what we've done in the past, so I can give you any sort of application problem. Yes, question? How many times that event will occur in that genome? So here we said how many times will that sequence appear in the genome. We had the probability of the event times the size of the genome. So we suspect it should happen on average about 10 times in that genome of that size. So it's always probability times genome size is how many times it will occur. But since it's an equation, you could work either way, right? Okay? You could say, if I want it to occur 10 times, and I know I have this, then well, then my probability has to be that over that, okay? So you can figure that out, all right? So let's quick do the sequencing part. Sequencing is extremely difficult to understand, okay? I'll try to help you with it, okay? There are some key points. I will try to really stress these. We have a large, okay, I have to clarify this. We can now sequence single molecules of DNA, but that's not the technique I'm going to be talking about, although that's the wave of the future, but it's not what we're talking about because it just gets too complicated. So we're going to do traditional sequencing, which is where we are using a large population of identical molecules. We'll talk about the primer. We've discussed it before, how it targets where we start and how it creates a 3' hydroxyl group. I'll show you that again and again. DNA polymerase will extend the DNA. We know that from PCR, and it has to have that 3' hydroxyl group, which is what the primer is doing. DNTP versus dideoxy. So a DNTP is a typical building block in DNA. It's a ribodeoxynucleotide triphosphate. DD is dideoxy, which means it's missing another oxygen relative to the deoxy. So there's ribose, which has 2 OH groups. There's deoxyribose, which has only 1 OH. And then there's dideoxy, which doesn't have any OHs at the 2' or 3' position. Okay? And I'll show you the structures. And then we use gel electrophoresis to separate our products, so we know them by size and how well can we tell those apart. So let's just look at a few things. This seems pretty straightforward, but let's spend a little bit of time on it. We have a template strand. We must have a template strand because we have to base pair with it. So without a template strand, you can't do sequencing. So the template strand in our experiment will be our PCR products. The primer, let's say this is the primer. It creates the 3' hydroxyl group. It is anti-parallel. And an incoming nucleoside triphosphate, let's say this is a DNTP. Now it's not an RNTP, because if it was an RNTP, what would be at this position? OH. It's a ribose. But it's a deoxyribose. So the bases have this solid numbering. So this is going to be numbered 1 carbon, 2 carbon, 3 carbon, 4, and the 5th carbon is there. Okay? And these get primed. So that's a 1' position, 2', 3', 4', 5'. We always talk about